And this is my review sheet. Okay, so what I've done is broken down each exam's materials for you into what I consider areas where you might see what I consider calculations and those that are just conceptual. Now, if I'm studying for this exam, quite frankly, the exam one material, I mean, by now, you shouldn't have to go back and really do much there. I think by now you should be able to answer a couple questions on significant figures if there's anything on there, because you've done it in lab and you've been using that. You know, things like ions, you should know by now that, you know, sodium forms a +1 cation and typically an oxygen -2, things like this. You might look over a few things, but don't spend a lot of time on exam one material. Dimensional analysis is something you've been using all semester. You don't have to go back and look at this now. Unit conversions, metric system, stuff we've been using. So I don't expect you to have to spend much time here. Exam two material, remember, oh, there's a bunch of chats. Let me make sure they're just not, yeah, oh, we can hear you. Yes, LRC 221, that's correct. And it should be posted on the D12 web page. It's there. Look at my news items, but it is LRC 221. Make sure you know where that is. You're not wandering around 5:59 Friday night looking for it, okay? Go find it. All right, exam two material, remember, is just chapter 3. That's it. And there's a bunch of stuff there that you you don't really need to go back over. Like I said, you're not going to be doing calculations with the Bohr equation, okay? And you're not going to have to answer all the nuances of Schrodinger and waves and shapes of orbitals and things like that. What comes out of exam two material that's critical is the way electrons behave and how they fill in atoms. So electron configurations, knowing what it means for an electron to be in an excited state, you know, orbital diagrams with the arrows and knowing the spins and how they match, right? Spin in opposite directions within orbital, how they fill. Most of that comes down to, when you think about this, we have 5 exams of material. We basically have what? 9 chapters? And I forget how many questions there are, but it's less than 35. I think it's 32. Could be 30. But we basically have 9 chapters. So what are you looking at? 3 questions per chapter, right? So for you to pick out 3-4 questions from a chapter, from exam 1 material, I can honestly tell you, that's 2 chapters. There's going to be little to nothing there, okay? You might see questions here. And what that means is something like this, you know, an isotope. Something like that, how many neutrons, protons, electrons, right? There's not going to be much from there. So figure you've really got 7 chapters covering most of your material. If you eliminate the first 2, okay? 4 questions per chapter. When you look at exam 2 material, and I'm asking 4 questions from there, heck, you better believe you're getting electron configuration, maybe 2, right? Maybe one's of an element, maybe an orbital diagram. Periodic trends was another major thing, right? Make sure you know your trends. That's pretty easy to study. Just memorize the trend, you know, increases up and over with electronegativity, things like that. Electronegativity really is the next material. Ionization energy increases up and over. Just know those trends. That's pretty easy to study that and read that and get your memory kind of recalling. So don't worry about all the nuances of quantum theory, right? Okay, focus on electron configurations and periodic trends and how electrons fill and behave. Go to exam 3 material. You'll probably have to name something, or, you know, pick the formula that matches the name, whatever. Lewis dot structures. We could give you Lewis dot structures and say which one of these is valid. You're not going to be drawing them, obviously. This is multiple choice. But that is, of course, Vesper and Lewis dot is exam 3 material. That's all of it. Chapters 4 and 5, right? You're going to get molecules and be asked for the shape. You're going to be asked if they're polar, right? You're going to be asked for electron Lewis dot questions like how many lone pairs, things like that, ways we can ask it so you don't have to draw the structure, but we know that you know the correct structure. You're looking at 4 questions from that material. I'm looking at polarity. I'm looking at molecular geometry, VSEPR. I'm looking at Lewis dot, right? Maybe formal charges. Honestly, don't remember if there's a formal charge question on the exam. But you want to know formal charges to help you anyway get to the right Lewis structure, right? So you're going to review that because you got to make sure that you can draw a correct Lewis structure. Because if you can't draw a correct Lewis structure, you can't answer the question on Lewis structure. You can't answer the questions on VSEPR either. And that's the whole section. Then you come to what I consider the heart of the calculations from Gen Chem 1, starting with stoichiometry. Okay? And that means being able to look at a chemical reaction and tell me what's limiting, how much product will form, right? Being able to do an empirical formula, percent composition, all of this. And then you've got on top of that, the solution stuff. So that's chapter 8, where you've got molarity on top of moles. Of course, moles is used, and that's introduced. I should have had that bold. That's introduced where in chapter? It was actually introduced in exam. There it is. It is bold. Exam 1 material. Moles, of course. But you're using that. You're going to be using that. We probably won't ask you just a simple question, how many moles, you know. You're going to be using that in your stoichiometric calculations, in your molarity calculations. A dilution, that you can probably see one of those problems on questions on dilution, possibly. There might be a straightforward one, just balancing, and that's it. Just don't remember if we ask it like that. Net ionic, I don't know. I mean, if it's on there, there's one question. I can't remember if it's on there. It's one of those ones where I wouldn't put on the final, but I don't get to decide the whole final. But certainly be able to do a calculation like limiting reactant, how much product is formed given this amount of this and excess of this, right? What's the molarity of the solution? All of that. And then, of course, you got the solubility guidelines in there also. And you're given that table. So just know how to use that table, okay? And decide which of these is going to form an insoluble precipitate. Which of these is the least soluble? That type of thing. And then you've got the last material. And now if I'm studying and you did good on this last exam, I don't need to study this much. I'm going to review a little bit of it, maybe an area that I was weak in. I'm going to spend most of my time studying this and then reviewing my electron configurations and periodic trends, right? Because exam 5 material should be pretty fresh in your head. Of course, if you bombed it, then you might want to spend some more time on exam 5 material. But gas laws are easy. You got PV equals nRT, right? And then Dalton's law. And he's giving you those formulas. So those are more plug and chug. Just know how to calculate a molar mass and a density if it goes that direction. I've got an example one, I think, on my review sheet where we take it to molar mass. And then enthalpy is always important because it comes back in Gen Chem 2. So we tend to emphasize that. A lot of people like to ask questions in thermodynamics is your enthalpy, and then in Gen Chem 2, your entropy and free energy. It's a major concept of general chemistry, period. So be able to do one of those specific heats or know what enthalpy of formation is. And this is an area that students struggle with. I just know from doing this for many years that enthalpy, this heat, not the gas laws, but chapter, I guess it's chapter 9 that students struggle with. So depending on how you did and how you feel with that. But once again, realize that you're going to get no more than 4 questions from this whole section, which means 2 gas laws, right? And 2 enthalpy questions. If you look at it like that. All right, so let's take a look at the actual questions and do some of them as a way of reviewing the material. Any questions right now about the format of the exam, what you can expect? Roughly 30 multiple choice questions. Okay, so now some of these might seem easy to you, and that's because, quite frankly, you're a lot smarter now than you were 13 weeks ago. You've covered this stuff. So some questions will seem simple to you if you're strong in that area. The number of unpaired, I like your hat, by the way. I'll give you some bonus points for it. The number of unpaired electrons in the gaseous selenium atom. You have to know a lot to do this, believe it or not. You got to be able to know the order of filling. You also have to know that Hund's rule of pairing them up and all of that. So you're going to want to do this in terms of like an orbital diagram is the best way to do it rather than electron configuration. You could do the electron configuration, then think about it from there, but I like to do an orbital diagram. I'll do the electron configuration. Of course, the abbreviated thing takes me through argon, right? Because I'm looking at selenium. Everybody know where selenium is? Right there, atomic number 34. So I'm good through argon, which is, of course, 18 electrons. And selenium has how many? 34. So I'm going to make sure I get the 34 electrons, make sure I don't make a mistake. I got 18 already, right? And then, of course, that's through argon. Then I've got, 4s2, 3d10 is all filled, right? So I can write that down. And then I've got the last, how many is that? That doesn't even look like a 2, but it is. It came out really sloppy. So that's, right, 30 electrons right there. I only got 4 left. So let's go ahead and write the 4p4. Now you might say, oh, there's 4 electrons. No, but you got to realize the p, the way they fill, right? So if you just look at that, you could do all of this. You don't need to do all of it, but 3d, 4s, oops. Probably not big enough actually for D. Three D, 4s, and 4p, right? And the D's filled, we know that. Spin up, spin down, they pair like that, right? 4s is filled. And then you fill these one at a time. So there's your answer, right? Number of unpaired electrons is what? 2. Okay. You don't need to do all that work to get to that if you're good with electron configurations. A lot of you are going to look at that and say, okay, it's filled 3D, 4s is filled 3D. I got 4 electrons, 3p, boom. 2 of the p boxes are filled. You just do this right here, and you've got your answer. And the answer is 2. Okay. So review doing some electron configurations and orbital diagrams, and you'll be good for any of those types of questions. Do review, though, how to do the ions. We ask you for electron configuration of iron 3. Remember, the transition metals lose the s electrons first, the highest principal quantum number. Okay? So if they ask an ion question, if we ask an ion question, review that definitely, how the ions form and which electrons come out first. Questions on that? Okay. Okay, for the second one now. Empirical formula. Someone tell me my jingle. That's close, right? What's the first step? Percent to mass, mass to moles, divided by smallest, multiplied to whole. Right? Percent to mass to moles, divided by smallest, multiplied to whole. So we've got 3 elements here. This is long for a final. You won't see 3 elements. You'll only see 2. Even my exam, I think I only gave you 2, right? But I did 3 just for practice. Gives us more to do. So sodium, 54 grams times in the molar mass of sodium, I have it right here, is 23 grams per mole. This is the area I told you, be careful with not taking enough digits and not rounding off too much. because you could get the wrong answer. So I really should have took more than 3 sig figs, but it works out okay for this one. And then for sodium, for boron, we've got what? What's the percent? It's 8.5%, so 8.5 grams. Times, and boron's molar mass is 10.8. And then we've got oxygen, and the percentage there is 37.5, so 37.5 grams times, and of course 16 grams per mole. That one is good with 3 sig figs because it's 15.9999. Oh, that's a 1. Is that 8.8 or 0.1? It is 0.8, okay. And that's 1 mole. That's my percent to mass, mass to moles, and I've done these already, so 2.35 moles you'd wind up with, 0.787 moles, and 2.34 moles. You see 2 of them are real close together. That's a trigger that they're going to be the same, right? In our final, that's percent to mass, mass to moles, divide by smallest. And then we will multiply the whole if we need to. Sometimes you don't need to. And for that, we get numbers of 2.99, of course, 1, and 2.97. These are approximately 3. So we're good. We are done. It is Na3 BO3. Percent to mass, mass to moles, divide by smallest, multiply to whole. No need to multiply to whole. Those are close enough to 3. Questions? Okay. Now, the next one, I give it like this as a study guide. It's a little bit too much for an exam if you've got to draw 4 Lewis structures. But sometimes there are some like this on the exam because it's more difficult. It's difficult to come up with questions that are avoid being Googleable. What is the Lewis structure of this? And you can just Google it. But if you've got 4 or 5 of them, good luck with time. So, plus, of course, you're in a room for this one with people walking around. But even for our release, that's kind of the way we thought about things. All right. So, which molecule has exactly 2 unshared lone pairs of electrons on the central atom? Starting with A, BF3. What do you know about boron when it comes to octet rules? I told you about the 2 Bs, boron and beryllium. They often do not have complete octets, right? So real quickly, BF3, 7 times 3 is 21, plus boron, which is in group 3, that's 24 electrons. Boron not getting an octet, you should automatically say to yourself, okay, this is going to be this, right? 8 times 3 is 24. Done. Boron doesn't need its octet. So this question is making sure you know how to do Lewis structures, that you recognize exceptions to the octet rule. That's why these questions are designed, multiple concepts built into one question. You got to know how to do Lewis structures. You got to recognize that boron has exceptions to the octet rule. Everybody okay with BF3? 24 electrons. How did I get that? Group 7 for fluorine, 7 times 3 is 21. Group 3 for boron, 3, 21, 3, 24. Octets for the fluorines, 8 times 3 is 24, done. Moving on to B then, OF2. So I got 7 and 7 is 14. and 6 is 20. This is a halogen attached to oxygen, very similar to the way hydrogen's attached to oxygen. It's going to look like water. Only difference is the fluorines are going to have octets instead of the hydrogens having just the 2 electrons. So you have your answer already, basically. We're still going to do the other ones. Right? 2 lone pairs. That's what the question asked. Which molecules exactly 2 unshared lone pairs of electrons on the central atom? We got 8 and 8 is 16 for the 2 fluorines, and then 2 lone pairs is 20, so we're done. No double bonds or nothing like that, right? Move on. We're going to double check, make sure. NF3, once again, halogens look just like hydrogens. This will look like just like ammonia. NH3, only the fluorines will have octets instead of 2 electrons. And you should realize, okay, right off the bat, it's only have 1 lone pair, right? We didn't do the total number of electrons, but we got 7 times 3 is 21. And then 26, because nitrogen is group 5. 8 times 3 is 24. That's a quick way to figure out lone pairs, right? Say to yourself, 8 times 3 is 24. I got 26. That means 1 lone pair on the nitrogen, right? Can't be the right answer. When you get done enough Lewis structures, you get good like that, you can just do that and say, okay, nitrogen can't have 2 lone pairs around it. It's got 3 bonded atoms, right? It's got to have its octets. It's going to have 1 lone pair. Questions so far? So it looks like B's our answer. I mean, yeah, B's our answer, but we're going to do D also. This is one you might not have seen. These other ones are a little bit more common. Xenon difluoride here. Okay, so you're always told that noble gases don't form compounds. They don't in nature, but we can make this compound no problem. We can make a lot of compounds with our noble gases as the central atom. So xenon, of course, has 8. And then you got your two fluorines. 7 times 2 is 14. 22 electrons, right? So I'm thinking to myself, okay, well, I'm only going to have 16, right? 16, 18, 20, 22. Done. Those are the rules, right? And you keep adding them to the central atom as long as it can take more than an octet, which xenon can because it's below the second period, right? You don't do double bonds. It doesn't call for double bonds. You use double bonds when you run out of electrons, right? That's when you start doing double bonds. You don't have enough to give octets. This is, hey, I've got extra electrons, just dump them on the central atom. You're not going to get any molecules that don't have a single central atom on the final exam, okay? That's more advanced Lewis structures, which is fine for an hourly, but not for a final exam. So based on our question then, B is our answer, because this has 0, this has 1, and this has 3, and this has 2. This is a study question. Be a little bit more condensed and quicker probably on an exam, but Lewis structure is one of those things we expect you to be pretty comfortable with. It's a major topic. Okay. All right. 4. This is just kind of a basic molar Avogadro number calculation. A typical silicon chip has a mass of 2.3 times 10 to the minus 4 grams. A silicon chip you might find in electronic devices. Assuming it is pure silicon, how many silicon atoms does the chip contain? Okay, so you've got mass. Yes. Oh, yes, I'm sorry. So I did that as a study guide. What is the molecular shape? Is it a polar molecule? Very good. Thank you. Hirsch's keeping tabs on me, so I'm slipping up. No, I put that there to study as a way as a study guide. It's not, it's not, this is not all structured as multiple choice. So we can look at all of these. A, what's the molecular shape? What's that? Trigonoplanar, right? Don't go by the Lewis structure. It looks like T-shaped, right? Those are all going to be spread out equally around the boron because there's no lone pairs. So it's trigonoplanar. So is it polar? No, right? Because they all cancel out. It's symmetrical. This is what we said. There are polar bonds, right? Because fluorine is very electronegative, but because the tug of war idea, right, we talked about, this isn't going anywhere in an electrical field because the one fluorines, you got to remember it's trigonoplanar. One's pulling this way, one's pulling this way, which gives you like a net of that way, and then this one's pulling that way. They cancel each other out. So it's non-polar trigonoplanar. How about B? Bent, right? Who said that? Carter, right? Carter's right. Bent, just like water, it's going to be bent. It's going to have those two lone electron pairs up top, pushing the fluorines down. Is that polar? Absolutely, right? So that's polar and bent. How about C? Tetrahedral with one pulled off, right? Get that trigonal pyramidal, right? Not bipyramidal. That's the one where you get into 5 pairs. So this will be trigonal pyramidal, and it will be polar. Absolutely. You got these highly electronegative fluorines. Nitrogen's electronegative too, but still electronegativity of fluorine is greater than nitrogen. So you're going to wind up with like a net dipole of kind of like one pulling this way, one pulling this way, one pulling this way, a net dipole in that direction. And the last one, I'm forgetting now. 3 lone pairs and 2. Is that linear? So if you pull off the 3 equatorials, right? Go to that table in our book. Page is that? Where it's got all of the Vesper. Here it is. That's hybridization. There it is. 5 linear, right? I was right. That's the molecular. I asked for molecular shape, so that's a molecular geometry. So remember, you got the 3 equatorial and the 2 axial. You pull off the 3 equatorial, and you wind up with a linear molecule. So non-polar because that's very symmetrical. All right. Other questions? Other things I forgot. All right. So we've got 2.3 times 10 to the minus 4 grams is what we're starting with. And we want to know the number of silicon atoms. So what's my first step? Dimensional analysis. Grams to what? Moles, right? And it's pure silicon, so we just take 28.1 grams per mole. And of course, Avogadro's number will be on your constant sheet. You have to memorize it, but 6.02 times 10 to the 23rd atoms per mole. And we get an answer of 4.9 times 10 to the 18th. Hey, better get a pretty big number. You're asked for the number of atoms, right? It's always large when you're asked for the number of atoms. Questions on that one? Okay. All right. 5. This is a gas law one, but it does the one I said. It's asked for the molar mass. What is the molar mass of an ideal gas? If 0.622 grams sample of this gas occupies a volume of 300 milliliters at 35 degrees C and 789 millimeters of mercury. This is probably a little long for a final exam question. We usually got to convert all of the units. Mils is easy, obviously. Just move the decimal place 3 places. Temperature and pressure. So if it was a final exam question, probably 2 of those would be in the correct units. And you only have to worry about 1 of them, something like that. It's typically what we do. All right, so PV equals nRT. What do we have? We've got volume 0.300 liters. We've got temperature equal to 35 plus 273, 308. And then we've got, what else do we got? Pressure. Pressure is equal to 789 millimeters of mercury times 760 for 1 atmosphere. And that gets us 1.04 atmospheres. So I've converted my things. I'm missing pressure. So if I calculate the pressure, I'm sorry, I'm not missing pressure, I'm missing moles. We just did pressure. P equals nRT, so I'm missing moles. If I get moles, I should trigger myself to realize, hey, I've got this mass here, and I'm asked for a molar mass, and molar mass is just grams per mole, right? So all I have to do is get moles and take the grams they gave me and divide it by moles and have my molar mass. So I don't make the mistake, N is equal to PV over RT. If you write these out, you're less likely to get them mixed up and do something backwards. So N is equal to 1.04 atmospheres times 0.300 liters. Of course, you'll have R, that'll be given to you on your constant sheet, 0.0821 liter atmospheres per mole Kelvin. And then I need temperature, which is 308 K. And this gives me 0.0123 moles. And now I can simply take the mass, divide by the moles to get my molar mass. Oops. $50.1 grams per mole. Notice how I did this problem though. I wrote down what I knew. I did my conversions. I wrote the actual equation down that I'm going to use. I wrote the rearranged equation down so I don't make the mistake of just doing it in my head. Even though it's easy to do in your head, it's easy to just swap to a bend. If you're just looking at that N equals P over RT, you're much less likely to make that silly mistake. And I get that a lot in classes like Gen Chem 1 and 2. Students coming up to me after an exam saying, stupid mistake. I should have done, I knew how to do this, You eliminate those types of things when you bring your grade up. Eliminate those silly mistakes. When you know how to do the math, you know how to do the problem. You just make a silly misstep. Questions on this one? Okay, 6. The combustion of C3H8O with O2 is represented by this balanced chemical equation. You've been given formula masses, molar masses. That's one way to speed things up on exams. You don't have to worry about doing those. When 3 grams of C3H8O and 7.38 grams of O2 are combined, how many moles of carbon dioxide form? So someone first tell me what type of problem this is. It's not, it is a combustion reaction, but you don't need to do that combustion analysis. It's stoichiometry, but specifically limiting. You have to figure out which of these is limiting because you're not told you have not equal masses. You have masses of both. You don't know which one's going to determine how much product forms. Okay. Combustion analysis, quite frankly, is too much for a final exam. You know, it's one section in that chapter, and it's the application, and it's advanced application of stoichiometry, you know, and it's more of an empirical formula, right? Using combustion analysis to figure out what the formula is. This is stoichiometry and specifically limiting reactant. Anytime you're asked how much product formed, how much reactant is needed, that's going to be stoichiometry, not empirical formulas. If this is combustion analysis, would have said, what's the empirical formula of this hydrocarbon? But if we do an empirical formula, it's not going to be combustion analysis where you've got to subtract out the oxygen. The hydrocarbon will not have oxygen in it if we do that. So the way we do limiting, we say, let's just do, right? Mass of A to moles of A, moles of A to moles of B. And it's only asking for moles, so I don't need to go to mass of B. And it's asking for CO2, so that'll be my B. And I'll simply calculate it for both reactants. And whichever one produces less moles of CO2 is my one that's limiting. And therefore, that will be my answer. So if I do 3.00 grams of C3H8O times mass of A to moles of A, I've got the molar mass, 60.1 grams in 1 mole. It's mass of A to moles of A. Moles of A to moles of B, I'm comparing this to this, 6 moles of CO2 for every 2 moles of the carbon compound. That'll give me that answer. And then I do the same thing for oxygen. 7.38 grams of O2 times, of course, 32 grams in 1 mole. Same numerator, 6 moles of CO2, different denominator, because I'm now comparing these two, right? So it's going to be 9 moles of O2 over here. And I've got these numbers calculated, so we get, where do I have it? So we get 0.154 up here. And down here we get 0.150 moles of CO2. We usually make them so that you can't see it by looking at it. We want you to do the calculation. Some of these you can say, oh, I'm supposed to have a 2-to-1 ratio. That's clearly not 2 to, and you can do it without doing the math. This one, they're very close. You can't tell unless you do the math. So the question is, what's my answer then? Well, we go with whichever one produces less. That means the oxygen was limiting, and then therefore that is my answer. So mass of A to moles of A, moles of A to moles of B, and then compare them. Take the one that's less, and that's your answer. Sometimes the questions will say, which is limiting and how much is produced? In this case, yes, did I make a mistake? Oh, really? Oh, did I do it backwards? Maybe, hang on. Oh, yeah, I did it backwards. No, so everything's fine. What I did, I just swapped these numbers, that's all. Yes, thank you. So this one, the oxygen is 0.54, right? Thank you. Oops. And this is 0.50, right? Which changes, right? It's important because it changes our limiting reactant. So the answer is the same, 0.150 moles of CO2, but now what you realize is the limiting one is C3H8O. And sometimes questions are worded like that. They'll ask you what's limiting and how much is produced. Yeah, thank you. I just got those swapped. Other questions? Okay, let's take a look at 7. Given this is a really good question. I like this because it requires you to know several things. Use this information to calculate the heat of formation. So, double check, make sure there's nobody chatting in a question. And there isn't. All right, so you have to know what the heat of formation is. You have to be able to write that. And then you have to know what Hess's law is and use that. And then you have to know how the enthalpies tie in, how you're going to have to add them up to get to the answer. So use this information to calculate the formation of SO3. So now we have to write that reaction. That's what's not given to you, the reaction that you need. So someone tell me what this is going to look like. What would a formation reaction for sulfur trioxide be? Hydrogen gas?
Or not, sorry.
So dang, how are we getting there? Plus oxygen gas, right? So we're going to need, this is what we're after. Sulfur plus oxygen gets me SO3. So we need to balance that, right? What is it? Right, 3/2 oxygen, right? We can't do it with adding anything. We can only form 1 mole. So we got to make sure that we're going to form only 1 mole. So that is right. Abigail's right. We need a 3/2 in front of the oxygen. That means we get 3 oxygens, right? And 1 sulfur. That's what we're after. Now we have to say to ourselves, okay, is everybody comfortable with that right there? How we got that? Remember, you have to form 1 mole, so you can't balance it by having 2 sulfurs, right? You can't multiply that by 2 and have 2 sulfurs, 3 O2s, and 2 SO3. That's one of the rules of a formation reaction. You have to only form 1 mole. Okay. Now we have to manipulate those top 2 reactions to add up to the bottom reaction. So what would we do to these? What do you want to do the first one? Flip it, right? Reverse it or flip it. So effectively, we're saying we're going to multiply this by -1. So that's going to give us S plus O2 goes to SO2. And we're going to have a negative 300 kilojoules. How about the second one? One half, right? Times it by 1/2. Very good. We need to get that times 1/2. So that will give us SO2 plus 1/2 O2 goes to SO3. Add this all up. There's the sulfur coming down. The SO2 cancels out. SO3 comes down, and 2/2 and 1/2 gives me 3/2. So that means, I didn't write the number out here. Since we multiplied it by 1/2, we now have negative 100 kilojoules. And then our answer is negative 400 kilojoules for the formation reaction of sulfur going to SO, formation reaction for SO2. So we had to write that formation reaction. We had to know what a formation reaction is. We had to use Hess's law to manipulate those, and then we had to know how to manipulate those enthalpies and add them up to get to the correct answer. Questions? Yes, Mary. Do what with whole numbers?
So like, I remember doing like, I think it was a video or something that's all where you multiply everything by 2, so you're not adding 3 halves.
Right, but that's, yeah, you can't do that in this case because, I mean, you could, and then in the end, divide the whole thing because of, this is the key right here. A formation reaction is for the formation of 1 mole of SO3. So you can go ahead and multiply this all by 2 to make it comfortable on your eyes, right? So if you multiply it all by 2, you have 2, you'll have 3, and you'll have 2. Then you'll manipulate these to get this with whole numbers, realizing in the end, you'll have to take that number that you get, you'll wind up with negative 800 as your answer. And you'll have to say, okay, well, that's for the formation of 2 moles, for 1 mole would be negative 400. Yeah, so that's why I don't do that with whole numbers here, because it's formation. Other questions? Yeah, go ahead and do that at home if that makes you more comfortable with the whole numbers. Because it's okay. It's not wrong to do it that way. You just got to remember that last step of dividing by 2 at the very end. Other questions? An atom has a valence shell electron configuration of NS1. To which group of elements in the periodic table does it belong? So it wants like a group name rather than just saying, you know, group 3. It wants the name of that group. So tell me what the group number is. 1, right? That's the alkali metals. Alkali metals. Group 1 alkali metals, group 2 alkaline earth metals. And then, of course, you got your noble gases and your halogens. Chalcogens, but I never learned that one, and I don't think we ever asked that, so don't worry about that. All right, what do these have in common? If you say the same number of proteins, you're really messed up. If you say the same number of protons, I'll be really annoyed. Because if it's the same number of protons, it means they're the same element, right? So it can't be the same number of protons. What do they have in common then? Yeah, most likely it's going to be electrons. You got to figure it out. It could be neutrons. You just got to make sure they're not going to be the same size because they have different nuclear charges, even though, so these are neon, right? Fluorine, ions, so isoelectronic, right? And magnesium's lost 2. So they all have 10 electrons. Magnesium has 12 that has lost 2. They all have 10 electrons. Fluorine has 9, but it's gained 1. It's the fluorine anion. And neon has 10 electrons to start with, and it's not an ion. Same number of electrons. They're not going to be the same size, even though they're isoelectronic, because they have a different nuclear charge. Remember, the larger nucleus pulls the electrons in a little bit stronger, more. It's like stronger magnet, stronger attraction. So they won't be the same size. So it should be the same number of electrons. I thought it was later. All right. We good? No. Look at magnesium on the periodic table. What's its atomic number? right? You're looking at the mass number. Yes, magnesium's 12. You look at the top number, the atomic number of protons is the same number as the electrons. The 24 is the number of protons plus neutrons, right? So magnesium has 12 electrons to start with, lost 2, now has 10. Fluorine has 9 to start with, gained 1, now has 10. Neon has 10 to start with. Anything else? What volume of 12 molar HCl is required to prepare exactly 500 mils of 0.6 molar HCl solution? Now let's double check. I'm pretty sure that's on his formula sheet. There it is there. M1V1 equals M2V2, right? So you have that on the formula sheet. This is the dilution one. You know, the book might have had it as, I said this before, initial and final, I's and F's, or it might have had it as dilute and concentrated. These are all the same. Don't be perturbed by that. So it wants to know what volume of 12 molar HCl, which means the initial volume, right? The V1. So you now have 12 molar times V1 is equal to prepare exactly 500 mils. All the answers are in milliliters, so we don't need to change anything. Times 0.60 molar. That's all. Divide by the 0.6 molar, the molarity goes away. Divide by the 500 mils. I'm sorry, the other way around. Divide by the 12 molar, the molarity goes away. You're left with mils on the right, and your answer is what? 25 C. Okay. Questions on that one? All right. Consider the Lewis structure for CH3Cl. What is the best description of the molecular shape? Is this molecule polar? D is correct. And what? It's draw it. It's tetrahedral. Carter's right. Is that going to be polar? Yeah. It's going to be polar because you got that one different group on there and it's highly electronegative. So we're not going to cancel out. So if you think of it, this is drawn, you know, in 2 dimensions. So it's incorrect to say that these 2 cancel out. But the idea is that that chlorine is, you have to look at the sum vector of those 3 hydrogens will be much smaller because of the low electronegativity of the hydrogens compared to the chlorine, but you will have a net dipole in this direction. If they had all been hydrogens or all been chlorines, then this would be nonpolar. You good? All right. Now, I didn't give you molar masses here. On an exam, you would have molar masses. And obviously, I'll just give them to you right now. But a 0.473 gram sample of phosphorus was reacted with excess chlorine. So you know right off the bat, it's not limiting. What is the yield of PCl5? That's all we want to know is what's the yield. So that's kind of like the theoretical yield because this is what's on paper. That's always the theoretical yield. Actual yield is what happens in the lab. That's going to be given to you. All right, I've got the molar masses of all these written down. So all we have to do is say mass of A to moles of A, moles of A to moles of B, moles of B to mass of B, since all the answers are in grams. So what do we got? We have 0. I guess I'll do it down here. 0.4 0.73 grams of P4. That's one of the forms of phosphorus, natural state. Plus, oh, not plus. We're doing dimensional. We're doing mass of A to moles of A times the moles of PO4. P4 is 1 mole. I just had 4 times the 30.97. That's the molar mass of phosphorus. Don't have it worked out. I just had it like that. That's mass of A to moles of A. Then use my stoichiometry. What do we ask? PCl5. So yes, 4 to 1 is what I'm looking at here. 4 moles PCl5 for every 1 mole of P4. And then we just need the molar mass of PCl5. So it's times 30.97 plus 5 times 35.5. That's chlorine divided by 1 mole PCl5. You do have to calculate a molar mass. Sometimes it's easier just to do it all in one step like this rather than just adding it up. And we get, I think it's C. Yes, 3.18 grams. Mass of A to moles of A, moles of A to moles of B, moles of B to mass of B. Questions? A compound consisting of an element having a low ionization energy and a second element having a high electron affinity is likely to have, I didn't even cover coordinate covalent bonds. It's not a topic that's typically covered in Gen 10. It's in your book probably. We just don't cover it. So you got one element that has a low ionization energy. Someone tell me what ionization energy means again. Energy it takes to steal that electron or lose that electron, right? So if it has a low ionization energy, that means it's something that gives up electrons easily. And where's that on the periodic table? Left, right? The metals. You can even say bottom left would be easier because you're even further from the nucleus, but in general, the left, the metals on the left. So we know we have a metal, and it's going to be on the left. And second element having a high electron affinity. And that's easy to know what that means because the words tell you electron affinity, affinity for electron. Where are the elements on the periodic table with high electron affinity? Top right, specifically right, the top right for sure. So we're looking at maybe something like, potassium chloride would fit this bill. So we can say ionic bonds. Covalent bonds would be more sharing. So say maybe something about high ionization energy and a low electron affinity would be more covalent. Might be like a metal that's further over here, or a metalloid, or 2 nonmetals, right? Metallic bonds are the bonds within the metal elements, like iron. You have a hunk of iron, not iron chloride, that would be more of a polar covalent bond, iron chloride. But iron, magnesium, the actual metals, those are metallic bonds. Really briefly talked about those as having kind of a sea of shared electrons. Questions? And then, of course, a molarity question. You got to expect some sort of solution questions. Molarity is a big concept. What mass of sodium hydroxide is necessary to make up 400 mils of 2.5 molar solution? Oh always write out your molarity as the units, I think, break it down to its moles per liter, and you'll be able to see dimensional analysis a little bit better. You say to yourself, I've got 2.5 moles per liter, and we need grams, basically, of sodium hydroxide, right? What do I do? Yeah, we're gonna need the molar masses of sodium hydroxide. What else do we need to multiply it by? The mils, right? The volume. So what is the molar mass? It's like 40, I think, for sodium hydroxide. It's 40 point. Yeah, it's pretty close to 40 grams per mole. We definitely want grams in the numerator because we're asked for grams over here. That gets rid of moles. I still got the 400 milliliters, put that as 0.4 liters. I get rid of liters. I have my answer. Turns out, just by coincidence, that 0.4 times 2.5 is 1, so you wind up with 40. You need 40 grams, which is the molar mass. Just a coincidence. But just look at your units in dimensional analysis. You're starting with moles per liter. You need to get rid of moles, get rid of liters, and get to grams. The only way to get grams is have your molar mass.